Hi, Dr. Saab. Good afternoon.
Sir, namaskar. Good afternoon.
How are you?
आई एम फाइन सर, थैंक यू। आप कैसे हैं?
मजे. How is the weather in Jammu?
सर बहुत बढ़िया मौसम हो रहा है, सर्दी हो रही है काफी। और पिछले 2 दिनों से धूप निकल रही है, ये नई चीज है।
Okay.
हाँ
Please,
हाँ।
please. Sir, I am calling you on your mobile phone. You are not picking up the call.
सर मैं देखता हूँ। सॉरी सर, मैं उठाता हूँ 1 मिनट।
Good afternoon, everyone, and welcome back to afternoon session of day 2 of ongoing 1 week-long faculty development program on information and communication technologies for smart city applications, ICT4Smart 2021, organized by Department of Electronics and Communication Engineering, NIT Silchar, and is sponsored by AICT New Delhi under ATAL FDP scheme. As a last speaker of day 2 session, Dr. Ravikant Saini from IIT Jammu is with us for delivering a talk. Dr. Saini received the BTech degree in Electronics and Communication Engineering and MTech degree in Communication System from IIT Roorkee, Uttarakhand, India in 2001 and 2005 respectively. After completing his PhD from IIT Delhi in 2016, he worked as an assistant professor in Shiv Nadar University, Greater Noida, India, till December 2017. Currently, he is working as an assistant professor at Department of Electrical Engineering, IIT Jammu, India. With this, I welcome and invite you, Dr. Ravikant Saini, to start the session.
थैंक यू सो मच डॉक्टर तैमूर for such a nice and warm welcome. So, as you are aware, we are going for this FDP program, which has been specifically designed for smart city applications. From the perspective of communication technologies, I will be sharing with you my views on utilization of terahertz communication systems.
Sir, you please share your screen.
All right. So
On bottom right side,
yes.
one icon present now. Bottom right side present
Right,
now.
right. That's there, sir.
Okay, okay.
So kindly please let me know if the screen is
Yes.
visible.
Yes, now it is visible. Make it slideshow and please go ahead.
So how do they move to the full screen presentation?
Simply press F5 from your keypad. F5.
F5. Yes, I am trying F5, but it's not working. Mm,
It is not
Not
coming.
it is not really coming up good.
Okay. Process is same, I think. Function F5. If you have function key on your keypad, function F5.
Okay, so what I will do, just give me a minute. Let me see what could be the issue.
Yes, yes, yes.
So I am just stopping this thing. Stop sharing for a while. Let me come back and let me try to do. Okay, so what's the issue here? This is here, and then if I do F5. Okay, so F5, when I'm doing F5 on my machine, it is converting it into
No, no,
this.
no. You are having Linux in your system.
Yes, yes, line machine, Linux it is, right?
I don't know how to proceed with the Linux.
Okay. No
Normal
problem.
MS Office, we usually do that one. No,
Okay.
after clicking on
That's
that
it.
person, now that it will be treated as it is, I think.
Just let me know now. Is it good?
Now, yes, now it is comparatively good. You go ahead with this one.
All right. So good afternoon, everyone. Thank you so much to Dr. Taimur for giving me this opportunity to share my views on smart city applications. So what I'm going to talk about is uh, possibility of utilizing terahertz communication in smart cities. So what we are going to talk about is a specialized communication zone, which has been kind of thought for utilization in smart city application. This is going to be uh, based on terahertz based communication technology, which has been envisioned for 6G communication systems. Here is the brief outline of the talk. We'll be giving you a brief introduction of what smart city, what terahertz is, then state of the art, what right now, from the perspective of communication systems, what are the things that are currently available, then what are the channel models that are available right now, the issues, say, for example, in terms of signal losses, what are the noise models available, then what are the signal propagation methods, then we'll talk about signal processing techniques like modulation and coding techniques, then optimal cooperation, possibility of utilizing cooperative communication in terahertz communication, then we'll summarize the future research directions, and then just share the references for the talk. All right, so as we are right now aware that we all are having smart devices all around us, be these our mobile phones, our say laptop devices, These are very basic things that we know that these are smart devices, but these are not the only one which are smart devices. These days we have smart, say, smart TVs, smart ACs, smart washing machines. See, everything is coming to smartness. So what this smartness is actually, if you just go back and check what this smartness means, then this smartness actually just means that the devices are able to connect to a Wi-Fi module, and they are able to share the information. And now the question comes, like, why are we going forward for connectivity of these devices? So we want to actually take care of all the devices, take control of them through smart applications. And just with the applications, we are able to actually revolve all other devices around us in a manner that creates kind of a personalized world to somebody. So it's like there are so many devices around us, and then they go just the way I want them to. So we have smart applications with our phone, within our phones, and then with these phones, with these applications, we are able to control these smart devices. Now here comes a very crucial point, which I'm just hinting here. This is called instant connectivity. That actually we want that the devices should be connectable to Wi-Fi devices, and then I should be able to control them, right? So this is a very crucial point, because you may be having devices but you are not able to connect to them. So the connectivity of the devices is a crucial point, and that's what the talk is going to be focusing about. How do we ensure connectivity? What are the things that have been considered for improving the connectivity of these devices? How do we improve the connectivity of the devices? So the takeaway from this slide is that we are in a kind of a personalized world where we are having a lot of devices which we can control with our mobile phones, and they are just helping us to feel as if we are in a personalized uh, world in itself. All right. So as we are getting smarter day by day, then there comes a possibility of coming up with a smart urban civilization where everybody is smart. So with the smart people, we have smart issues. So everybody wants to have smart transportation. So smart transportation means like these devices, the transportation mechanism. It's not like you are going to stop on the, you know, on the bus stop and you are waiting for the bus, whether it is coming, when it is coming. So the smart transportation, just to give you a like simple use case, will be you will be knowing, okay, the bus for this route is coming, say within say next 2 minutes, right? So this is a simple example of a smart transportation. Then smart housing, you are having a household which has got smart devices, as we have indicated, say smart ACs, which can run on based on your requirements. So the moment you enter, say in your house, once you open the lock of the door, then the devices can be alert. They can say, they can feel, okay, my owner is back home, so let us switch on the lights, let's switch on the AC, let us switch on the particular say a TV program that he's very much interested in seeing the moment he reaches home, right? Then next use case is smart office. So the way we have smart house, we can think of coming up with smart offices, which could be like to the next level of the physical offices that right now we are having. Then next is smart healthcare, where we are trying to imagine, like instead of worrying that you may be aware of this thing called telehealthcare, where there is no need to go for like a medical practitioner just right away. You can talk to him, you can just have a video call, video chat, and then there are certain sensors nearby you, around you. The doctor can easily see those sensors, the data of those sensors, and then he can kind of give you advice. The first side, I would say first sample of advice, based on which a lot of things can be improved. Then smart water, smart electricity, smart grid, you are aware of that. Very many people are these days talking about smart metering, smart grid communication. Smart grid is altogether a very different field, evolving right now. And then smart waste management. So how do we because as we tend to create waste, so how do we manage our waste in a smarter manner? So there comes this use case of smart management, and these are just a few of the things that we can think of coming up with the smart civilization. So with these use cases assembled together, we are coming to a picture of smart city. So we actually need a smart city for the smart people who are going to live in there to improve their overall, quality of life. All right, so let's move on to what is a smart city. So smart city is assumed to be a self-sustained adaptive infrastructure. So what is self-sustained means that it is complete in itself, and it's an adaptive infrastructure which varies based on the input demands. Input based on the inputs, it will actually varying itself. So this is not a static structure; it's a dynamic structure. It's a dynamic, dynamic infrastructure which keeps on varying based on the demands. Then it has to be supported by the information and communication technology, because the devices, as we will be talking about, are required to communicate with each other, right? And the third thing is automation. So what people are coming up with, that can we think of coming up with automation, more and more of automation in the devices, more and more of automation in the use cases, where, say for example, instead of things being handled by uh, manual efforts, which could lead to the possibility of getting certain errors. So if we can think of coming up with automation where the devices are actually themselves taking the decision, and then they are uh, taking the call on their own, right? So smart city is considered to be a vision where devices are taking control of the things on their own without any human or least human interactions. Now, what is Internet of Things? So we are aware of internet, like this is kind of network of computer devices. Usually, we used to consider it to be like that, but gradually the things have evolved. In between, we had this machine-to-machine communication. Then came this idea of Internet of Things, where they say that it is not Internet of machines, it is not Internet of computers, it is actually Internet of Things, where the simple common household or even simple devices that you see near in the neighborhood, in your near vicinity, or smart devices, and they can like talk to each other, they can talk to the central authorities, they can talk to the processing units. All right, so the network of these smart devices contains actually usually kind of three kind of devices. One are sensors, then controllers, and then actuators. So what are sensors? So sensors are those devices which actually sense the certain parameters, and then they will be feeding this data to, say, some controlling device. The controlling device is going to perform certain actions, certain algorithm on this data which has been sensed by the sensors, and then based on this decision that the controller takes, actually it will be doing certain action, and then that action will be actually uh, reflected with the help of the actuators. So in one sense, IoT is kind of a bridging gap between the physical world and the digital world. How do I say it so? Because the physical world is where the sensors are actually collecting the data, and then digital world is where the information processing is actually happening. So these IoT devices are having front end, which are like devices which are collecting the data, and front end also contains those devices which will be affecting certain decisions, so which comes under actuators. And then there will be a very strong connection between the devices which will come to the digital world. So with the growing age, growing time, we are having devices in and around human. So uh, what does this mean is that very gradually we are coming to certain times where devices are there, nearby us, kind of wearable devices. Say for example, one is a pulse reader. Many of you are aware of this. So yeah, you can wear it as a wristband, right? And then this can help you get very basic information regarding, like, say, pulse reading, temperature, pressure, kind of these things. And then the next end could be sophisticated medical reporting system. So this leads to the, like, other extreme of the devices, where devices are actually maybe embedded inside the body, and they are reading critical information about a patient. And these information, this set of information is being reported to the medical practitioners for maybe record purposes, and maybe so that the person is kept under observation by the medical practitioner, and he may take necessary action as and when required. All right. So smart devices actually needs smart communication techniques. So because we are getting so many devices and they wants to communicate, so we need to come up with smart technological solutions so that they could communicate effectively, easily. So there comes this concept of smart communication zones. So what we are actually trying to think of is that there is a possibility. Can we think of coming up with this? We consider it like information super highways, where we say that devices could connect with each other at a very fast speed. So as we will be talking about, like, terahertz communication actually gives us the possibility of coming up with, say, terabits per second of data rates. These are the data rates that are imagined for terahertz communication systems. So what are the challenges when we are talking of possibility of coming up with communication zones? These communication zones is that there is an increasing number of devices. This, as you all are aware, that even in home the number of devices are increasing. Even outside, the number of devices, smart devices who wants to communicate, are increasing. There is an intensive increase in the internet transactions that these devices are doing, actually, because they wants to communicate. That's why they want to share their information. And then there is heterogeneity of devices, means there are very simple devices like sensors, and there are sophisticated devices like, say, so for example, your mobile phone and your desktop, right? So they also wants to connect to the devices. They also wants to connect to the Wi-Fi hub. So how do we connect all these together? So there is a need of coming up with a communication zone. Since the devices are pretty dense, so you can think of coming up, okay, can we come up with a cluster of devices, and then we say, okay, these all devices are considered under one zone, and they will be served by certain certain Wi-Fi spot. And so the device density is large, the distances between the devices is small, and there comes a possibility of coming up with a specialized communication zone in terms of a cluster of devices. So there is a possibility of utilizing terahertz. So terahertz has a limitation that the device distance, the communication distances are not allowed to be very large. You can just communicate within, say, a range of, say, 10 meters or so, right? So we can think of coming up with communication zones which are, say, just typically within a meter's distance. And then we can think of coming up if feasible solution to the problem called last mile problem. If you are aware, there is this problem called last mile, which means actually that we could earlier provide high speed data connectivity up to the last hub, but not to the end user. The reason of this could have been, say, for example, say, in terms of, say, just a few days back, there were these high speed data lines, right? They were able to provide high speed data internet up to the access point, but the user was not allowed to get that much of high data rate. But gradually, with the fourth generation, fifth generation communication systems, this data rate has been improved. But this classical last mile problem just indicates that the end user could not be provided high data rate in terms of, like, gigabits per second. So this terahertz based communication zones actually kind of promises us to provide that high speed data to the end user. So these I will be calling them THISCOs as the acronym, terahertz based high speed communication zones. So these THISCOs provides us the possibility to solve this issue of high speed data connectivity to the end user. So this slide we have already talked about. This slide actually tries to summarize the use cases. So if we have these THISCOs available, then they will be able to help us achieve smartness in home, power, waste disposal, smart home, smart offices, smart healthcare, smart transportation. And these the bottom side you see in the left side, these are the issues that we will be going to talk about. What are the inherent issues uh, that we need to solve? One is the absorption loss, another is the small coverage, like the distances that we can communicate are not very large. Within 10 meters, that is the max that we can communicate. Then the possibilities are opportunities in terms of terabits data link. Then there is a possibility of massive MIMO also, because the frequency range is very high, wavelength is very small, so the antenna footprint is very small, and there is a possibility of you know uh, combine putting a lot of antennas together. So as we will discuss later, there has been discussions going for like 1024 transmitting antennas at the transmitters. So these are the investigations that people are actually going forward to. Okay, so the opportunities and challenges. So the opportunities are in terms of, say, the terahertz band, which actually ranges from 100 gigahertz to 10 terahertz. This gives us a very large bandwidth, say in the range of gigahertz, and then uh, we can get data rates in the range of terabits per second. Low latency means you can download the data in like in a fraction of like seconds. Reason being because the data rate is very high. So you can if you get say 1 tbps of data, then you can imagine like how much download time it will take for you to download, say, any video file. And the another opportunity is, say, smaller wavelength that we have discussed. So there is a possibility of utilizing massive MIMO. So massive MIMO, as we are aware that MIMO can be utilized for improving the spectral efficiency of the system, improving, say, utilizing the beamforming concept, and then we can think of improving data rate of certain user. But here, as we will discuss, data rate is not a big concern. Reason being because you're already getting terabits of data rate. So what usually people try to utilize MIMO for is, say, for improving the coverage. So they try to direct the beam to particular user. So there have been discussions regarding, say, utilizing beam for distance dependent users. So there is somebody who is nearby, there is somebody very far away. So can we think of utilizing beamforming there to improve the data rate of the users? And the challenges for the terahertz communication zone specifically are generation and detection of terahertz signals. So we will be talking about this. This is a very critical issue. If we are not able to generate well, if we are not able to detect terahertz signal, then what to think of like communication systems? Then there are unfavorable propagation characteristics, like the signal doesn't flow as good as the normal communication systems. And we need to think of like there are issues like atmospheric absorption. Then the channel properties also we will discuss. What are the issues? That the channel properties are really not as good as they happen to be at the lower frequencies. Okay, so this slide actually kind of gives us a summary of what is the state of art. So we'll be talking about terahertz electronics in terms of, say, signal generation, signal detection, and amplification. Physical layer technology, we'll be talking about some modulation and coding techniques, channel coding techniques, beamforming like MIMO techniques, and then channel modeling. What are the models available? So propagation models, deterministic and statistical approach, and then what are the noise models? Okay, so let's come to terahertz generation and detection. So usually this gap is the frequency band from, say, 100 gigahertz to 10 terahertz. This is usually called as terahertz gap. I tell you the reason, because this particular bandwidth is sandwiched between microwave and infrared frequencies. So on one side, people are actually looking forward to electronic devices. The issue here is that since the frequency is very high, so the electron does not get enough time to reach from source to drain, because the polarity is changing very fast. And because of this, there is very less current. So that is one end of the problem. And the other end is, if we are looking for the photonic devices, there is issue that it is very difficult to control the discrete energy levels and to come up with devices where we could get signals or data. We could get electromagnetic photons. We could get photons in this frequency range. So both these sides are having issues, but people are actually trying to solve certain things, and they have got some possible solutions. So say for example, one silicon germanium based transistor has been investigated for say 798 megahertz, and then gallium nitride based HEMT, high electron mobility transistors, have been investigated for the terahertz range, and they have been found to be usable. And people are actually looking forward to the uses of graphene also. And graphene has actually found to be providing better solutions for which actually has got a high directivity. So this has been considered suitably for wearable devices. So we'll be looking forward to this possibility of utilization of graphene. Now, in as a summary for like channel characterization, there are deterministic models, there are statistical models. So deterministic models means like these are as you are aware of two-ray tracing model. Two-ray model you might have heard of in say wireless communication, right? So similar thing has been done here for ray tracing model, but these are actually specific to environment. The detailed geometrical information is required for the environment you want to study, and the model will be specific to that environment only. These are computationally intensive but highly accurate. But the issue is the moment you put a small change in the environment, if you just like change one of the devices from here to there, then you need to do for a recalculation, and then you cannot predict how the model is going to behave. For a specific geometry, it will give you very accurate model of the channel, but it's not. It's kind of recommended only for indoor environment which have got kind of a pretty defined pattern of the devices, pretty defined geometrical information. But it cannot be utilized for outdoor environment which varies with time very fast. So let's discuss this statistical models. So instead of looking forward to the deterministic, people started looking for statistical models. We need to study like different multipath components, then kind of coming up with this tap delay line model. And then the studies are actually based on like angle of arrival of the multipath components, angle of departure of the component, time of arrival of the components, like that. So the noise that we find out in terahertz communication is uh, we are aware of this like white Gaussian noise. We say that is like the thermal noise that we all aware of, because the electrons are random, and then they create random noise which we summarize, and then we say okay, it leads to thermal noise. But here there is another kind of noise, that is molecular absorption noise. So just to give you an idea, what happens is when the signal gets is moving through the medium, then the molecules absorb the energy of the signal, and then once they absorb the energy, then your signal strength is going to die down, and then they will move from like lower energy level to higher energy level, and then they will come back also. When they come back from higher energy level to lower energy level, they will be releasing this emitted in the form of like emission photons. They will be emitting, and then this leads to a random noise which you are not which is called as self-induced noise, because this came because the signal was there. So they call it as self-induced noise because the signal came, the molecules got from lower energy level to higher energy level, and when they are coming from higher to lower, they are emitting this random noise. So this is a typical problem for terahertz communication systems, and because of the absorption, you will find like the distances of communication distances are not really very high here. Okay, so the physical layer techniques that we are going to talk about are modulation techniques. So because the channel has got distance dependent behavior, people have investigated this on-off modulation, simple on-off modulation system. And there are issues like whether we should go for a single carrier or we should go for multiple carrier. Okay, in terms of coding techniques, there are there are two things. One is error prevention, another is error correction. So usually what we find is there are, in fact, there is one thing called error detection also. So what we usually in our conventional communication systems, what we usually do is we have forward error correction systems or we have error detection systems. So say for example, if you are aware of parity bits, so they are just like error detection mechanisms. So once you know, okay, the error has occurred, so you will just request the transmitter, okay, you retransmit it. That's error detection. Then error correction is, okay, you have received the packet, then based on your channel coding strategies, which code you have applied, then you can think of coming up, okay, we can think of improving 1-bit error correction, 2-bit error correction. Based on that, you can think of doing away the effect of the channel noise. But here the issue is, they say that is it required to go for decoding? Is it required to go for retransmission? Can we think of coming up something called error prevention, that the error should not occur at all? So these are the things that people are actually thinking in terahertz communication system. Instead of imagining to go for error detection and error correction, they are actually trying to come up with error prevention, and we'll be talking about what are the things that that people are actually looking forward to. Massive MIMO techniques, these are known to have high spectral efficiency. We know that because the frequency is very high, lambda is small, so there is a possibility of utilizing a large number of antennas, and beamforming can actually be utilized, as I have indicated, to overcome the issue of short distance communication. All right, so now we'll be talking about a few of the issues of the channel. So so the first part that we are going to talk about is in the under the category of channel models. We will be talking about losses. So okay, let me briefly tell you what a channel model is. Usually, channel model is a mathematical representation how the signal behaves as it moves through the medium from the transmitter towards the receiver end. So what are the things that it will face? How will the amplitude change? What are the changes that it will face once it moves from transmitter to receiver? So usually, there is this trade-off whether we should go for a simple channel model or we should go for sophisticated channel model. So simple channel model is required for analytical study because analysis is easy when we consider just a simple channel model. But sophisticated channel models actually takes care of all the possible effects that the signal is facing, and it is traveling from transmitter to receiver. So these sophisticated channel models are actually required when you want to go for a practical implementation of the things, because the simple is just good for theoretical study, lab study, but for the practical implementation you need to actually have sophisticated channel models. So we are going to discuss a few of the basic properties of this terahertz channel. The first is the spreading loss. So spreading loss is like the loss that once the signal propagates through the air, it will be losing its energy. So this is the free space path loss formula that you are all aware of. This is given by question 1. Then there is second thing which is called absorption loss. Absorption loss is actually that part where the air molecules absorb the signal energy, and it is given in terms of absorption coefficient. So here this absorption coefficient actually takes care of the mixture of the medium. What are the different gases? What are their percentage? What are the different components of that medium? Based on that, this absorption coefficient is calculated, and then based on that, this absorption loss is found out. In terms of noise model, there are two things. One is the background noise that we are all aware of. This depends on this, because of the random movement of the electrons, as we are aware of background noise. So the formula is given by equation where Kb is the Boltzmann constant, T0 reference temperature, B is transmission bandwidth, KTB. This is the formula that we have been using. And then F is the sky noise acceptance factor, and then epsilon is the emissivity of medium. Absorption noise is once we are transmitting the power um, from the transmitter, then absorption noise is that part, because the signal moves, then these molecules will move to the higher layer and then they will come back. So according to the transmitted power, that much amount proportional to that, they will be releasing the noise. So this as you appreciate, this absorption noise 4 actually depends on the power that you are putting in the medium. So in one sense, they say that if you are not putting any signal, there is zero noise, zero absorption noise, then there will be just background noise. But since you are causing this noise to happen because of your signal only, that's why this is proportional to the transmitted signal. So these are the two basic noises that are available in the terahertz system. The signal propagation, as you are aware, once the signal moves from, say, transmitter to the receiver, then it can either have reflection. There is a possibility of that you can have a line of sight communication from transmitter to receiver. Otherwise, it can get reflected, it can get diffracted, and scattered also. Okay, so reflection is pretty, very common, because you may anyway find any surface which will be reflecting the signal. Diffraction may not occur depending on whether between the transmitter and receiver there are sharp objects or not. And scattering is pretty prevalent here in terahertz communication, because the scattering actually depends on the size of this device, the scatterer, the size of the scatterer. As the scatterer size reaches closer to the wavelength of the signal, the scattering becomes predominant. So what happens here is the even the smoothness, or I would say roughness of the wall, roughness of the environment, that comes closer to the wavelength. So what happens is, if something was is behaving as a reflecting surface for lower frequency signal, it starts behaving as a scatterer for terahertz signal. So scattering is a very predominant phenomenon in terahertz communication systems. Okay, let's go one by one. So this slide kind of summarizes the transfer function of a reflected wave. So if there is a wave, and it is say from the transmitter, there is a reflector at a distance of r1, and then from reflector to the receiver the distance is r2, then this equation actually summarizes what is the transfer function of the reflected wave, right? There RF is the reflection coefficient, which has been given by equation 6, and this depends on Fresnel reflection coefficient and the Rayleigh roughness factor of the medium. Similarly, this is diffraction model. So how do we obtain the transfer function of the diffracted wave? Though diffraction is not a very predominant factor in indoor channels, because usually you will not find very sharp objects available, but it is still studied, right? And scattering is the biggest issue here, because the wavelength is of the order of surface roughness, as I have already indicated, and then scattering is very predominant here. And this is the way of handling. How do we take care of the scattering of the signal? What is the transfer function of the scattered wave? All right. So now we discuss the signal processing techniques. What are the modulation techniques that have been considered for this terahertz communication systems? So the physical layer techniques, as we know, should be actually viewed around the channel properties. Based on the channel properties, depending on the channel behavior, depending on the channel statistics studies, we actually plan what is the good modulation technique that will work here. So based on these studies, a simple on-off modulation was studied. A pulse represents 1, and a no signal represents 0. And in order to distinguish that the zeros with the silence zones, there was utilized the preamble to identify that, okay, now the transmission starts, and to indicate, okay, now it is no transmissions, right? In order to avoid that gap, so a preamble was utilized, and there was a fixed time between successive transmissions. So uh, like suppose we are transmitting certain bits, so uh, each bit has certain fixed duration of time, and during that entire time, just a small fraction was utilized for pulse transmission. So there were actually this has got two advantages, two benefits. One is that once you fix that the transmission time is fixed, then there is no need of synchronization. The receiver will exactly know that at what time it should receive the signal, because once it is able to, because the timing between the bits is fixed, already fixed. Once you have synchronized to one bit, then there is no need for further synchronization, and you can just listen to the receiver at particular, say, gap of t. At every t you will be getting a signal. That's the thing. Another thing is, because the pulse duration is less compared to the bit duration, I will be telling you, like in the, probably, yes, in the next slide it is there. So because there is a gap, okay, let's move to the slide itself. So this is the example that I'm going to talk about. So what is happening here is, there are two transmitter, tx1 and tx2. This is the pulse duration, and from here to here, this is the slot duration. So this pulse here indicates that I wish to transmit one. So what I wish to transmit from transmitter 1 is 1101, and there is tx2. The possibility of tx2 comes because, see, within this slot duration, for this duration of time, the channel is free. So I can think of utilizing this for multiple access. So I can add like user 2, user 3, user 4, depending on like what gap I am able to have here, and accordingly those many number of users I can accommodate. So this is the system, simple system that we are actually discussing, on-off modulation system, and this works well. So this bit duration are fixed, like this time is t from here to here, this time is t, but because it is a 0, so there is no transmission here. From 0 to 1, again this time duration is going to be ts probably, right? So okay, because this duration is fixed, that is one thing, and then there is a gap. This allows us multiple access, but this scheme has one issue. The issue is, if tx1 and tx2 somehow collides, because there is no central authority going to tell them how do you communicate. So if tx1 and tx2 somehow accidentally transmit at the same time, then all their data, right, this is 1101, this is 1110, so all their data is going to collide. So everything that they are transmitting is going to mix up, and you are getting collision at all particular slots. So all slots will lose their data. So as an improvement to this technique, actually somebody said, instead of doing this slot duration fix, can we think of varying it? So this is an improvement to the existing technique. What people did is, okay, for one they have picked up a duration of ts1, for another user they have picked up a duration of ts2. Yes, for this user it will always remain to be ts1, for this user it will always remain to be ts2, and if there is a time clash that they may tend, if it happens so that they may tend to transmit at the same time, then there is a possibility that only a few of the bits, but not all, will be lost. So this was suggested as an improvement to the modulation technique for this, for the terahertz communication. Now there has been discussion on this thing, whether instead of using a single carrier system, should we go for a multiple carrier system. So what people have found is that since the channel behaves, depending, channel has got distance dependent behavior. So people actually came up with, okay, there are communication windows based on communication distances. So if device is very nearby, then you can think of utilizing a broader window. Then device is very far, then you can think of utilizing say smaller window. And then these windows may be utilized for, say, multi-carrier communication. So people have actually come up with terabits kind of data rates while utilizing this multi-carrier modulation technique and utilizing this MQM modulation over that. But here there is a trade-off, on the number of subcarriers, whether you should use lesser subcarriers, whether you should use more subcarriers, right? So more subcarriers issue is that the system complexity is going to increase. The lesser subcarrier issues, if there are if you think that I should use the whole bandwidth instead as a single carrier and not utilize as a subcarrier method, then there are issues like if there is a loss, because this is the same as single carrier versus multi-carrier modulation. If there is a loss, then all the data is lost if you reduce the number of carriers. So this trade-off is again there. OFDMA is not kind of a suitable technique for terahertz. Reason being, OFDMA requires a strict synchronization between the devices, and this requires pretty high, because you will be requiring these DSP chips which need to run at a very fast pace. So there is right now not the high-end processors are kind of right now not available. So because of this, OFDMA is not considered to be a suitable solution for this. Okay, so apart from modulation, coding is another area that we need to think of in terms of signal processing. So as we have already discussed this thing, error detection. So if you detect that there is an error, then you need to retransmit. If you feel you are utilizing error correction, then you need to decode the thing. And there are issues like decoding time, decoding complexity, decoding power, how much power you should utilize for decoding of the received bits. So instead, what people have thought of is coming up with error prevention. So what they are saying is, let us try to prevent errors instead of doing error correction. So what has been done is actually, in order to reduce the effect of noise, they have reduced the number of ones, which actually number of ones in a code is actually weight of the code. So what they are trying to do is, can we think of having lower weight codes? Can we think of utilizing lower weight codes that could give us the same error correcting capability? So it has been investigated that it is possible to come up with lower rate codes which can improve improve the performance of the system even in this noise environment also, right? So this is the idea. And going on this similar idea only, what they have done is they have come up with minimum energy channel codes. So here also the idea is same, that if we reduce the number of ones, then the average power of the code is going to be reduced. So they have tried to observe that the error correction can be improved. As we know that the error correction can be improved by increasing the Hamming distance. So what they have done is MEC codes which satisfies the minimum Hamming distance criteria are found to be like strong error correction capability. So it has been investigated for utilization in noisy environment of channel, terahertz channel. Based on the similar philosophy, minimum energy source code has also been investigated, where what people are saying is that when we are allocating symbols, some bit pattern, then very frequent symbols should be given a pattern which has lesser number of ones. So this will again help us in improving the overall weight of the system, as we know. So this has been investigated, and what they have done is the frequent symbols which are having very high probability of occurrence, they are allocated symbols which are having lesser number of ones. MIMO techniques. Okay, so terahertz wavelength, very small, so this gives a very small footprint, so we can utilize MIMO. And adaptive beamforming has been proposed here. Narrow beam can be actually utilized for a distant user, and this can help in against the losses of the channel, because we know that the channel has got very less coverage, and if a user is quite far, then we can think of coming up with a narrow beam which has been tuned only for that particular user, and this can help in improving the coverage of the system also. So what people have done is they have come up with adaptive power allocation strategies, adaptive antenna subarray selection strategies, which can cater to users at varying distances. So I have indicated this. So multiple arrays, multiple sub-arrays have been utilized to cater to users which are at various distances in order to take care of them. Further, the terahertz-based, plasmonic ultra nano antenna arrays have been investigated for the wearable networks, which has the flexibility that each element at the transmitter as well as at the receiver can be, independently tuned at the transmitter as well as at the receiver. All right. So now let us move to the possibility of cooperation. So what these Ciscos are, these are actually high activity zones, because there is a, within a small coverage area we have got so many devices and they wants to talk to each other. They wants to share information with each other. So we need to have a mechanism that the power utilized should be power utilization should be efficient, because suppose earlier there was a big cell which was taking care of, say suppose certain area, say for example 1 square kilometer, right? But now when we are talking of Ciscos, these are very small coverage areas which can just cover, say, certain square meters only. So if we are having Ciscos everywhere, then this will lead to like a high density of Ciscos. And if everybody is just everybody is required to actually to work at the optimum level. So in order to come up with the green communication systems where we utilize the power to the best optimal level, we need to come up with a solution where everybody utilizes its own resources to the best efficient manner. So the idea is we need to come up with efficient resource optimizations within each Ciscos, so that we don't because the density is going to be very high of these Ciscos. Further, we need to come up with a specific MAC design for the terahertz band. The usual MAC is not going to work, because the devices will be actually the devices will be communicating only for a small duration of time, and then they will be going to a silent zone, and they need to have kind of a mechanism where they could identify whether the channel is free, whether the channel is available, and when to transmit. Their communication distances are short and the data is very intensive for them. So this is the collision avoidance, how to avoid collision, how to handle the collision, this has to be studied. And the possibility of multiple access that we have already seen, there is a possibility of multiple access. Okay, cooperation and relaying. So since the communication distances are small, so there comes a need of utilization of relays. So relays can be utilized for improving the connectivity, for improving the coverage of the cell. And further, there is a possibility of utilizing neighboring nodes for transporting the information. So what we can think of is, we can think of coming up with clusters. So cluster is kind of a collection of devices where one of them is going to forward the data of the nearby devices to the next hop. So these things can also be investigated here. There is a possibility of utilizing relays, as we have discussed. So possibility of utilizing AF relay, DF relay, RF relay. And when we talk of relaying, then comes the issue of optimal resource allocation. How do we allocate resources between, say, the relay and the source? Power sharing. How do we do power sharing? And the next thing is the relay placement. Where should the relay be placed so as to improve the overall efficiency of the system, overall coverage area, and quality of service improvement, right? Okay, so now we are kind of close to the last part of the discussion. So what are the future research directions that we see as we move forward? So this slide kind of summarizes the four major areas. These are four major areas from the perspective of communication systems. One is channel modeling. So we need to come up with sophisticated channel models for the terahertz channel, and sophisticated channel models versus simple channel models that we have already discussed. Modulation and coding techniques. What are the possible modulation and coding techniques that can be utilized for this? Optimal cooperation and utilization of relays in communication zones. And the next point is communication security, that we'll talk about it. So communication security is, as we know, that the communication is prone to breach of trust. It's all in air because it is a wireless communication. So there comes a possibility of loss of information. So we'll be talking about what are the issues in communication security, and then what are the possible future research directions in this. Channel modeling. So what we are finding is that deeper channel investigations are required for indoor environment, as we have seen that there is a possibility of finding out mathematically intensive, channel model. But the issue is this model has limitations. It requires detailed geometrical information. Further, the moment you give some change, then the total model changes. You cannot predict how it is going to behave. So we need to come up with certain models which could actually handle certain amount of randomness, which could predict, okay, if we did this, then how it going to behave now. That kind of predictability should be there. Then we need to investigate how are the different materials available, say in indoor environment. How are the different surfaces going to behave? Is it going to be a reflecting surface, or it is what are the properties with respect to this surface, say from the perspective of scattering? So deeper investigations are required how the different materials behaves for terahertz channel. And then we need to similar studies are required for, say, outdoor channels also, because indoor channel environment is quite easy in one sense, because there are no there are no random changes there. So there is a well-defined boundary, and everybody or everything is just going to be within those boundaries. That's why this has got pretty defined definitions compared to an outdoor environment. Outdoor environment has got a lot of randomness. You have no control over the environment because things are moving, because the environment is changing continuously. So you need to come up with a model which can think of modeling the terahertz communication channel for outdoor environment. And this further we cannot think of coming up with a deterministic model in an outdoor environment, because the environment is not static. This is a very dynamic environment, and so we need to come up with a statistical channel model for outdoor environment. And then this is going to be a time varying. This is going to have time varying behavior, as we know that the channel is not static. The model cannot be static. Model has to be like varying with respect to the changes, because the channel has got this inherent issue of varying behavior. All right. So from the perspective of variable networks, again, we need to look forward to how the signal behaves when it moves from, say, one organ to another organ, say, or even maybe we may be required to study how the signal passes through different tissues of the body. And since the body variable is going to be worn by, say, somebody, and then there will be it will be communicating with the next hop. But in between there comes this possibility that the particular say human organ may be moving. Say, for example, when you're walking, then your hands are moving. Say, similar thing is there with respect to, say, if you have a sensor, say, suppose placed in your shoes, then how do these devices connect with each other? So a sensor available in your hand versus a data collector available in your shoes. So this require deeper investigations further, because this is also a pretty random channel model, pretty random environment, and then deeper, say for example, different tissues are there, different bones are there. How do the signals communicate between them? So these require some more investigation in this direction. So how does the signal gets absorbed between different tissues, random movement of the different body parts that we have discussed, and can we think of coming up with a real-time channel simulator for terahertz communication systems? That is going to be a bigger achievement in the sense, because we will be able to simulate very many environment inside our labs itself. Say, be it indoor environment, outdoor environment, be it wearable network, and then based on the parameters, based on the status, based on the different settings, different parameters, we can come up with different testing environments for the protocols that we are going to design for them. So instead of doing real-time transmission and reception, we can think of coming up with a channel simulator, and then the proof of concept, the pilot studies, communication protocol based studies, they can be studied in the lab setup itself before bringing the things to the real time applications, before bringing them to the real world altogether. So there comes this possibility if we have the feasibility of coming up with a real-time simulator. All right. So in terms of communication techniques, we have indicated this, that femtosecond based pulse modulation, OAK, was investigated, but the issue here is that the pulse gets broadened. If the pulse get broadened, the issue is that broadened means it gets elongated in time. Then it is going to create interference to the neighboring users. Suppose my pulse was of say 10 milliseconds, then it gets broadened to 11 milliseconds, then it may interfere with the neighboring users data. So because of this, interference may come, and this may lead to like collision of the data, and then total rate of transmission may go down. So we need to come up certain we need to investigate how to what are the possible techniques, what are the possible solutions that we can think of utilizing here. And we need modulation techniques which can be evolved on the channel models. So because the channel, the modulation technique has to be actually tweaked based on the channel properties. So because the channel properties of the 10 terahertz band are not quite similar to those at the lower frequency band, so we need to have specific studies for the modulation techniques for terahertz band. Utilization of massive MIMO, but when we are utilizing massive MIMO, as we have indicated for say beamforming, there are issues say in terms of channel estimation, because you need to estimate for those many number of, because those many channels, we need to have estimate of those many antennas, because when you want to utilize say channel state information is required when we are utilizing say MIMO. So for this, we need to have a specific channel estimation techniques which could provide us reliable channel estimates. And then there are issues with respect to synchronization also. When we are having say 1024 cross 1024 transmission receiver system in a massive MIMO setup, then you can imagine like how much processing is required for synchronization, how much processing is required for channel estimation. You need to have like 1000 cross 1000 channel matrix, and how do we process it, and how do we communicate it from receiver to the transmitter. So these are the issues going forward which we should investigate when we have idea of utilizing massive MIMO in terahertz communication systems. Okay, in terms of cooperation and relaying, so we have discussed, okay, cluster clusters can be formed where nearby devices can request one of the one of the capable user to be a cluster head, and then he can think of kind of taking care of all the neighboring devices, and then think of sending the data to the next hop. But the issues is like which one should be used, considered as cluster head, what should be the size of cluster, how many cluster can we think of coming up, what should be the routing protocol, how much energy he is ready to offload, how much of his transmission capability, communication capability he is ready to offload for the neighbors. These are the issues that requires investigation while discussing the cooperation among the nodes. Okay, and then comes this question of congestion. So if we think that there is somebody a cluster, then because everybody is dependent on him, then the node may get bottleneck. So there leads to this possibility of getting congestion in the network. And if that node goes off, then you have further issues, because all the other nodes, all the other neighboring nodes, which were being taken care of by the cluster head, are actually lost. You cannot connect to them. So congestion is another issue. How to handle the congestion, and how can we think of once we identify, okay, that one of the node is down, how can we request another person to come up, and who should be selected for the next cluster? Handover between zones. The issue is, okay, this issue comes from mobility, because if there is a mobile device who is moving from, say, one TISCOS to another TISCOS, one communication zone to another communication zone, then because the communication distances are very small, so for a simple walking people, you may need to go for handovers, because the distances are very small. Now there are issues here. The reason being, the reason being the distances are very small, so the handovers will be very frequent. That is one thing. And then the issue will be in terms of, say, for example, latency. Latency is an issue because your data is being communicated to you, for example, and then within that fraction of time you are connected to some other Ciscos. Then how do we maintain the connection? Because if the person is moving, say, for example, at a good speed, then his handover will be pretty fast. And how do we maintain latency here so that his connection could be retained, his connection is not lost? So these are a few of the basic issues which we need to discuss more, which we need to actually research a bit more. Handovers, and then load. There is an inherent low latency requirement. How do we take care of person's own communication, his own communication? All right. Now the last part for the future research directions is the security concern. So as we know that IoTs are networks of devices, and these devices are from, say, different vendors, and they will be like reading data, sharing data with their own bosses. You might be aware of these issues, where certain devices are observed to be reading information, and then which as they say that they are utilized for your personalized accounts only. But this leads to this may lead to breach of communication. Okay, what are the key things which are required for secrecy of communication? One is confidentiality, integrity, availability of information. These are the key aspects of secrecy in communication. So what confidentiality is like? If something is intended, say, for example, X, per person X, then it should be only open to him only. It should not be possible that this information is available to everybody. Integrity means that the message which was sent for, say, for example, Mr. X, then it was not tampered with in between. It did not happen that, say, I have sent a mail, then in between it was stopped by somebody, and then he, instead of, say, I was writing yes, he wrote a no, and then he forwarded altogether to the next hop. So that is integrity. That means like the message was not tampered with. And availability of information, right? It's like, okay, suppose the information is available to you, the facility, the services that you want, they are available to you. Somebody has not blocked. If you are aware of this denial of service attack, right? It's related to that thing. And the next issue that we have to solve these things. And then the next thing that that I want to particularly highlight here is, because the devices are from different vendors, then how can we come up with a common platform where the devices from different vendors could share their data, and we could ensure, or we could come up with a some surety from their side that they are not going to misuse the data, even if they are getting this data from, say, certain vendor. Say, suppose for example, say some medical data, right? Medical data is taken care of by, say, a wearable device by some vendor X. Then we should have this trust from that vendor X that the data that his device is taking from a person, it should be utilized for his medical benefit only. It should not be utilized by somebody else. And if suppose that device is sharing that data with certain another vendor, then how can we think of bringing them together on a common platform, common trust platform, where they could believe that the data the device X has shared is correct to the best, right? Because the next bullet highlights like false information injection by a malicious node. If there is a possibility of false information injection, if somebody may think of like utilizing the possibility of using entering false information into the network, then in this case it may lead to the manipulation of the system behavior, right? So somebody can manipulate the data, and somebody can actually take control of the system. And another is identity verification. Identity verification is required for to avoid the cases of impersonation. And this may lead to leakage of data, because the person is not intended for that data, and he is trying to impersonate like somebody X, and then he is trying to get away with the data. So these are the security issues. The security issues are important because everything is information, everything is in the form of data, and it's available, say, at the device level as well as when the devices are communicating. So now we need a kind of a novel model where we can think of coming up with a trust platform where the devices could interact with each other, and they could be believed that these devices are taking the data only for the intended purposes. All right. So the security of IoT is really a big concern for all of us, because these are the devices that are going to come up like in the coming years, and we are going to be surrounded by such devices. So security of their data, security of in fact it is our data, security of data is a big concern for all of us. All right, so I think we are done with this. And I would just like to let you know that Terahertz, as we have indicated, is kind of a big opportunity in terms of communication technology, paradigm of communication systems. So what people are suggesting is that instead of evolving the current techniques, evolving the current modulation and communication techniques for Terahertz, people are suggesting that we need to give a fresh look from a different perspective, because this is altogether a different channel with its own requirements, with its own challenges. So instead of evolving the solutions which were designed for lower frequency bands. We need to come up with solutions which are specific to these high frequency bands. So these are a few of the references, and I think that's all from my side. Thanks a lot for your patience. Thanks a lot for listening to me. And if there are any questions, I would be um, trying my best to help you answer.
Thank
I'm
you,
done.
Dr. Shrikant Saini, for delivering a wonderful talk on terahertz communication in perspectives of smart city applications. There are few queries from the YouTube channel chat box, which I am
Sure.
passing to you. What are the possible effect of a small scale and a large scale fading?
Possible fading, he is interested, or he has written probably.
I think he has written in context of your specific PPT or some part of that one. What are the possible effect of a small scale and large scale fading?
Fading. Okay. So small scale fading is when you are stationary at certain location, but because of the multipath effects, you will be receiving randomness in the signal, because the multipath components are going to add up, and maybe constructively or destructively. So this is quite possible here. This happens here in terahertz. The way it happens in normal wireless communication, the same way it happens here also. And large scale fading, as we say that, okay, the way the channel is behaving with respect to the distance. So as we have indicated, these are short distance communication. The more closer you are to the transmitter, the better channel you are going to face. So the both these effects are there.
Okay. What are the effects on human when we apply terahertz communication system in body area network?
Yes, this is a very interesting question, but I would beg your pardon in the sense that I have not, I really don't have idea on the effect of terahertz signals over the body.
Okay.
How does it affect?
Okay. No problem. Next one is terahertz communication system suitable for low power wireless sensor network and battery operated network?
Yes, yes. So as I have indicated somewhere, uh, terahertz communication system is envisioned for say small distance communication, right? So devices which are close to nearby, say if these may be sensor devices, because this talk was about like IoT devices only. So people are thinking of coming up with solutions for smart devices which can communicate with each other at a faster rate. So a terahertz appears to be a possible solution for this.
Okay. Last query is terahertz communication is 6G communication?
Yes, yes. Terahertz is being considered for sixth generation communication systems. You are very
Okay.
right.
Okay. Okay. With this, we are very much thankful of you, first for accepting our invitation for delivering a talk, and second one for delivering a wonderful session in this 90 minutes duration. With this,
All right.
thank you very much, and
Thank
see
you.
you on the valedictory session also. Personally,
Right.
I am inviting you here, and
Okay.
formally, I will send the invitation to be available at 3:30 on 15th January for valedictory session, just for sharing your views. What was your experience in the entire period of this FDP?
Right.
Okay, thank you.
All
Have a
right.
nice
Thank you. Thank you,
bye.
everyone. Thank you so
Okay,
much. Bye bye. Take care.
okay, okay. Now, thank you everyone for joining us today. We will meet again tomorrow. Tomorrow session at 9:30 a.m. Till then, take care. Bye bye. See you.